Riemann Hypothesis. In 1859, German mathematician Bernhard Riemann published a short paper 8 pages that would go on to become the single most consequential unsolved problem in all of mathematics. The question he posed was about prime numbers, those whole numbers, like 2, 3, 5, 7, and 11, that can only be divided by themselves and 1. Primes appear endlessly as you count upward, but their distribution looks random. Riemann believed there was a hidden order underneath. He built a function now called the Riemann zeta function that encodes the behavior of primes. When you look at where this function equals 0, something strange appears. Every 0 found so far sits on a single straight line. Riemann hypothesized that all of them do. That is the hypothesis, and nobody has been able to prove it. Over 10 trillion zeros have been calculated by computer. Every single one sits on that line. But in mathematics, 10 trillion examples prove nothing. You need a proof that holds for infinity. David Hilbert listed it among the greatest open problems in 1900. The Clay Mathematics Institute placed a $1 million prize on it in 2000. Partial progress has been made. Mathematicians have proven the hypothesis holds under certain conditions, but the full proof has never arrived. Some mathematicians believe the answer lies in quantum mechanics, since the zeros of the zeta function behave like energy levels in certain physical systems. Others pursue a purely algebraic route through number theory. A third camp argues the hypothesis may be true, but unprovable within standard mathematics, which would itself be a result of staggering consequence. The Riemann hypothesis remains the most valuable unsolved problem in mathematics, and the line Riemann drew in 1859 has never been crossed. Collatz Conjecture. In 1937, German mathematician Lothar Collatz wrote down a rule so simple a child can follow it. Take any positive whole number. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Then repeat the process with whatever number you land on. The conjecture states that no matter which number you start with, you will always eventually reach 1. Try it with 6. Divide by 2 to get 3, multiply by 3, and add 1 to get 10. Divide by 2 to get 5, and so on. Eventually, you reach 1. Start with 27, and the sequence climbs to 9,232 before crashing back down to 1. Every number ever tested obeys this rule. Not one exception has been found. But no one can prove it holds forever. Computers have tested the conjecture for numbers up to 2 to the power of 68 a figure with 20 digits. It holds every time. Mathematicians have spent decades trying to find a structural reason why, but the problem resists every known method. Paul Erdos, one of the most prolific mathematicians of the 20th century, said about this problem, "Mathematics is not yet ready for such questions." Some researchers approach it through probability theory, arguing that statistically the sequence must fall. Others try to study it using dynamical systems, treating the rule as a machine and analyzing what the machine does over time. A more recent approach uses techniques from ergodic theory, looking at the long-run behavior of large sets of numbers rather than individual ones. The Collatz conjecture has been open for nearly 90 years, and the simpler a problem looks, the more suspicious mathematicians have learned to be. Goldbach's conjecture. In 1742, Prussian mathematician Christian Goldbach wrote a letter to Leonhard Euler, arguably the greatest mathematician of the 18th century, proposing an observation. Every even number greater than 2, Goldbach noticed, appears to be the sum of 2 prime numbers. Take 4, it is 2 plus 2. Take 28, it is 11 plus 17. Take 100, it is 3 plus 97, or 11 plus 89. Simple to state, simple to check, impossible to prove. Euler could not prove it either. He called it a theorem he was completely certain of, but could not demonstrate. That was 1742. The conjecture has been checked for every even number up to 4 times 10 to the power of 18 4 quintillion numbers, and holds without a single exception. The proof has never come. In 1930, Soviet mathematician Lev Schnirelman proved that every even number can be expressed as the sum of a finite number of primes, not 2, but a finite count, which was considered meaningful progress. In 1966, Chinese mathematician Qin Jingrun proved that every sufficiently large even number is either the sum of 2 primes or the sum of a prime and a number with at most 2 prime factors. That result, known as Qin's theorem, remains the closest anyone has come. Some mathematicians believe a proof will come through sieve theory, a technique for filtering primes out of large sets of numbers. Others think the problem requires an entirely new framework for understanding how primes are distributed. A minority position holds that the conjecture may be true, but structurally beyond proof, similar to certain theorems made unprovable by Gödel's incompleteness results. Goldbach's conjecture has outlasted empires, survived 2 world wars, and resisted every tool mathematics has produced, and it remains unproven to this day. The twin prime problem. Prime numbers, as you move further along the number line, appear less and less frequently. They thin out. But something strange keeps happening. Pairs of primes separated by exactly 2 keep showing up. 11 and 13, 17 and 19, 41 and 43, 1,000,007 and 1,000,009. These pairs are called twin primes. The twin prime conjecture, first formally stated in the 19th century, holds that there are infinitely many of them, that no matter how far you travel into the number line, another pair is always waiting. No proof exists. And the further you go, the rarer the pairs become, which makes the conjecture feel less and less obvious the more you examine it. The prime numbers themselves are infinite, but that tells us nothing about whether twin primes specifically go on forever. In 2013, a then largely unknown mathematician named Yitang Zhang produced a result that shocked the mathematical world. He proved that there are infinitely many pairs of primes separated by at most 70 million, not 2, but a finite gap, for the first time ever proven. Within a year, a collaborative project called Polymath reduced that bound from 70 million down to 246. The target is 2. No one has reached it. Most current work focuses on sieve methods tools for isolating primes within large sets. Others look to the distribution of primes in arithmetic progressions. Some mathematicians believe the techniques used to close the gap from 70 million to 246 could eventually be pushed all the way to 2, but the final steps remain unclear. The twin prime conjecture sits just 2 numbers away from being answered, and that gap of 2 has held for over a century. Every time water flows from a tap, every time wind moves around a building, every time blood moves through a vein, the physics governing that motion is described by a set of equations written down in the 19th century by Claude Louis Navier and George Gabriel Stokes. These equations model the behavior of fluids. They are used daily in engineering, meteorology, and medicine. They work. The problem is that no one can prove they always work. The question the Clay Mathematics Institute is offering $1 million to answer is this: do solutions to the Navier-Stokes equations always exist? And do they always remain smooth, meaning free of infinite spikes or breakdowns, no matter what conditions you start with? We can simulate fluids. We can measure them. But we cannot prove, mathematically, that the equations never produce a catastrophic breakdown. In 2 dimensions, the problem has been solved. Smooth solutions always exist. In 3 dimensions, which is where all real fluid motion happens, no one has managed it. Partial results exist. Solutions are known to be smooth for a short time after any given starting point. But whether they remain smooth forever, or whether they eventually blow up into mathematical chaos, is unknown. Some mathematicians believe a blow-up does exist, that under extreme conditions, the equations produce infinite values, which would mean they are fundamentally incomplete as a physical model. Others believe solutions remain smooth, but that the proof requires mathematics not yet developed. A third camp focuses on weak solutions, relaxed versions of the equations, hoping to work backward toward the full problem. The Navier-Stokes problem is unique among unsolved questions. The equations are used every day to build aircraft and forecast weather, and yet no one can prove they do not secretly break down. The P versus NP problem. This one is not about numbers or shapes. It is about the nature of problems themselves and what it means to solve them. Some problems are easy to solve. Some are hard to solve, but easy to check once a solution is given. The P versus NP question asks whether those 2 categories are actually the same. In formal terms, if a solution to a problem can be verified quickly, can it also be found quickly? If the answer is yes, if P equals NP, the consequences would be difficult to fully imagine. Most encryption used to secure internet traffic relies on the assumption that certain problems are hard to solve, but easy to verify. If that assumption is wrong, modern cryptography could collapse. Drug discovery, logistics, artificial intelligence, entire fields rest on the boundary between P and NP. The problem was formally posed in 1971 by Stephen Cook and independently by Leonid Levin. In the 50 years since, despite sustained effort from the world's best computer scientists and mathematicians, no proof has emerged in either direction. Most researchers believe P does not equal NP, that hard problems are genuinely hard, but belief is not proof. A 2010 survey of experts found that 83% expected P to not equal NP, with most admitting they had no idea how to prove it. Some approaches attempt to find problems that provably cannot be solved quickly, using techniques from circuit complexity. Others try to classify problems by their internal structure to find a separating argument. A more controversial position, held by a small number of researchers, suggests the question may be independent of standard mathematical axioms, meaning it could be genuinely unanswerable within the current foundations of mathematics. P versus NP is the one unsolved problem whose answer could immediately reshape civilization, and after 50 years, the answer is no closer. The Hodge Conjecture. In 1950, Scottish mathematician William Valence Douglas Hodge stood before the International Congress of Mathematicians and described a pattern he had observed in the geometry of complex mathematical spaces. In these spaces, which exist in dimensions far beyond what can be visualized, certain geometric shapes, called cycles, appear repeatedly. Hodge conjectured that these shapes are always built from simpler algebraic pieces. It was a claim about the deep structure of geometry itself. The conjecture sits at the intersection of three fields: algebraic geometry, topology, and complex analysis. This means proving it requires fluency across mathematical domains that rarely speak to each other, and a framework broad enough to hold all three together. No such framework has been built. Progress on the Hodge conjecture has been slow and fragmentary. It has been proven in certain special cases for specific types of spaces and specific dimensions, but the general case remains open. The difficulty is compounded by the fact that the objects involved are hard to compute with directly. Much of the work has been in developing new tools in algebraic geometry rather than attacking the conjecture head-on. Some mathematicians approach it through motivic cohomology, a framework designed to unify different notions of cycles across geometry and number theory. Others focus on specific classes of varieties where the structure is more tractable. A small number of researchers have argued that a counterexample may exist a space where Hodge's pattern breaks down, but none has been found. The Hodge conjecture describes something mathematicians can see and feel in the structure of complex spaces, but seeing a pattern and proving it are two entirely different things. The Yang-Mills existence and mass gap. In the 1950s, physicists Chen-Ning Yang and Robert Mills developed a set of equations to describe the fundamental forces that hold atomic nuclei together. These equations became a cornerstone of the Standard Model of particle physics, the framework that describes every known particle and force in the universe, except gravity. The Yang-Mills equations work. Experimental results match their predictions with extraordinary precision. The problem is that nobody can prove they are mathematically consistent. Specifically, the question is whether Yang-Mills theory applied to three-dimensional space actually has solutions that exist, and whether those solutions exhibit a mass gap, a minimum amount of energy required to produce any particle. The mass gap would explain why certain forces only operate at short range. Every physical experiment suggests it is real. The mathematical proof does not exist. The challenge is that quantum field theory, the mathematical language in which Yang-Mills equations live, is not fully rigorous by the standards of pure mathematics. Physicists use techniques that produce correct answers, but that mathematicians cannot formally justify. Building a mathematically airtight version of Yang-Mills theory from the ground up has proven to be one of the hardest problems at the boundary of physics and mathematics. Partial results exist in simplified versions of the theory, but the physically relevant three-dimensional case remains untouched. Some researchers pursue constructive quantum field theory and attempt to build Yang-Mills rigorously from first principles using probability theory and functional analysis. Others focus on lattice approximations, where continuous space is replaced with a grid, hoping to extract the continuum behavior in the limit. A third direction comes from string theory, which offers new geometric tools that may eventually reach the Yang-Mills problem. Yang-Mills is the only unsolved problem on this list where the answer is already being used built into every particle accelerator ever constructed, and yet the proof that it makes sense does not exist.